We're going to be continuing with acids and bases in this video, and I just want to do a quick review from previous material before we jump into this one. So we had differentiated between strong acids and weak acids, and we said that a strong acid is completely ionized. Right? If I was to draw or write a chemical equation for this, I'm taking my acid and I'm just using HA as a generic acid. It's going to react with water. I'm going to form hydronium ions, my conjugate acid, plus A minus, my conjugate base. And it is not a reversible reaction. I'm only drawing an arrow in one direction, right? My conjugate base here is actually not really basic, right? It's not going to accept a proton and go backwards. So we would say that it's inert, right? It's not reactive. So not reversible, we're not going to establish equilibrium. If we were to make a beaker drawing, right? I have hydronium ions, my conjugate acid, and I have A minus. You could throw some water in here if you wanted, but I don't have HA, right? This arrow only going in one direction. Because of that, I'm not going to write equilibrium constant expressions, right? Because it's not going to establish equilibrium. My weak acids, these are only partially ionized. Using HA again, just this time it's going to be weak. Water is going to act like our base. I am going to form hydronium ions and my conjugate base, but then that conjugate base does have an affinity for protons. It can accept a proton and go back in the other direction. Because of that, we can establish equilibrium and we can write an equilibrium constant expression for this. So my conjugate base, it is basic, right? It can accept a proton and go back in the other direction. If we were to do a beaker drawing for my weak acid, I would have some HA, hydronium ions, and my conjugate base, hydronium ions being my conjugate acid. It does, when we say partially, it's actually mostly unionized, so it's really, and this is still not to scale, much more HA, right? Much more of our unionized acid than hydronium ions and A minus. It's really generally only about 5%. Which means when we write our equilibrium constant expressions for these, my equilibrium constant is going to be a small number, right? Because it's only about 5% dissociated. My concentration of products is going to be much smaller than my concentration of reactants. So most of our equilibrium constants for these are generally going to be very small. We talked about pH previously, and we said that pH is the negative log of our hydronium ion concentration. We said that anytime we have an aqueous solution, my hydronium ion concentration multiplied by my hydroxide ion concentration is equal to Kw, which at 25 degrees Celsius is 1.0 times 10 to the negative 14th. Right? Water reacts with water to form hydronium ions and hydroxide ions. Because water is a pure liquid, and we write our equilibrium constant expression for this, right? Water is not part of that expression. So just hydroxide times hydronium. We said then whether a solution is acidic, basic, or neutral depends on the relative concentration of those, right? If my hydronium and hydroxide ion concentrations are equal, it's neutral. If I have more hydronium ions than hydroxide ions, it's an acidic solution. And then if I have more hydroxide than hydronium, it's a basic solution. pH then is just another way to express the hydronium ion concentration in solution. If we have a strong acid, and we can just use SA as an abbreviation if you want for strong acids, because they're completely ionized, whatever my strong acid concentration is my hydronium ion concentration, right? Because it's completely dissociated. If we go back and look at our equation here, right? This is going only in the forward direction. So because it's a 1-to-1 molar relationship, right? I have 1 mole of acid for every 1 mole of my hydronium ions. If my concentration of acid, let's just say was 0.200 molar, then my concentration of hydronium ions is going to be 0.200 molar, right? Whatever that strong acid concentration is initially is going to be my hydronium ion concentration. So because of that, figuring out the pH of strong acids is pretty straightforward. You just take the negative log of whatever your strong acid concentration is. For weak acids, it's a little trickier. So that's what we're going to focus on next in this video. So for weak acids, right, it's going to be a bit more involved. To determine the pH. Right? These reactions are reversible. They do establish equilibrium. If we go back up and look, right, I don't have arrows just going in one direction. Some of my HA is dissociated, but I'm also going back to form more HA. So how much of this do we have? Well, that's going to involve an ice table, just like we did in chapter 13, right? We need to figure out our equilibrium concentration of hydronium ions to determine the pH. So determining the pH of weak acids and weak base solutions is what we're going to work on next. So we're going to write kind of our steps. We're going to write what's called the acid dissociation equilibrium equation, which is just the reaction I wrote above. It's the reaction of my acid with water. It's just we have to have it a title, so when I tell you to do it, you know what I'm talking about. So if I say write the acid dissociation equilibrium equation, that is what I'm talking about. So let's just do another one. It's taking my weak acid, it's reacting it with water. Water is going to act like a base and accept a proton, forming hydronium ions, my conjugate acid, leaving me A minus, my conjugate base. So if I say write the acid dissociation equilibrium equation, this is what I'm looking for. We're going to write the equilibrium constant expression. Right, we're going to set that equal to our equilibrium constant. So capital K, remember, represents our equilibrium constant. And then I'm going to put a subscript A for acids. We're going to make an ice table. And then for determine the equilibrium concentration of hydronium ions. And then from that, to get the pH, you would take the negative log of your equilibrium concentration of hydronium ions. An example for us, we're going to calculate the pH and the equilibrium concentration. I'm abbreviating you now. Of all species for a 0.200 molar acetic acid solution. And acetic acid is H, CH3CO2, a very common weak acid. The Ka of acetic acid is equal to 1.8 times 10 to the negative fifth at 25 degrees Celsius. So our first step is we're going to write our equilibrium equation. So I have acetic acid. By definition, it's an aqueous solution. I'm going to react it with water, which is a pure liquid. Acetic acid is going to donate a proton to water. Water is acting like my base here to produce my conjugate acid, which are acetic or hydronium ions. And then I'm left with my conjugate base, acetate ions. Again, one of those polyatomic ions that you would have learned in 150 or 151. And then because acetic acid does have an affinity for protons, it can take a proton from hydronium ions, going back to form acetic acid and water. So this is our acid dissociation equilibrium equation. I'm going to write my Ka expression, write my equilibrium constant expression. So I know that 1.8 times 10 to the negative fifth. In fact, we're going to make an ice table. So I'm going to actually move this down a little bit so we can just make our table right underneath our equation here. So I'm just going to move it here. 1.8 times 10 to the negative fifth is going to equal my concentration of hydronium ions multiplied by my concentration of acetate ions, my conjugate base, over the concentration of acetic acid. We are excluding water. Remember, water is a pure liquid, and the concentration of pure liquids and solids don't change as the reaction proceeds, so that's left out. And then, of course, because I'm setting these equal to an equilibrium constant, I didn't leave myself much room here, but those are equilibrium concentrations that get plugged into that expression. So we're going to set up our ice table just like we did in chapter 13. So I is my initial concentration, C is my change, and then E is my equilibrium concentration. And again, if you prefer to just write ICE, that's totally fine. This is just how I've been doing it forever, and it's a habit that I don't really want to change. So initial concentration, my initial concentration of acetic acid was given to us in the problem. Water we don't care about, right? It's not part of my expression, right? It's pure water. It doesn't have a concentration, right? It's 100% concentrated. It's just water. Initially, I don't have any products, so 0 for hydronium ions and acetate ions. And then it's going to react. We're going to lose some unknown amount, so I'm going to call that X. I'm going to gain that on my product side. Remember that whatever number, right, if we need a coefficient in front of X, it's the same as the coefficient in my balanced chemical equation. So because I have coefficients of 1 in front of everything, it's just 1X. And then at equilibrium, what I started out with minus what we lost. For hydronium ions, 0 plus X is just X, right? What we started out with plus what we gained, and then also just X. We then take those numbers, we plug them into this expression. So X times X on the top, so X squared, and then on the bottom, 0.200 minus X. And then because we had said, if we go back up somewhere, right, that only about 5%, right, is ionized. Most of it is in the unionized form. So the amount of products that I have, right, is much less compared to the concentration of reactants, meaning my equilibrium constants are small, right? If I go back here, my equilibrium constant, 10 to the negative fifth. We had said that a small one is less than 10 to the negative third. So because this is small, we can use that assumption where my initial concentration, the amount that I'm losing, X in this case, is negligible compared to that initial concentration. So we can use the assumption that 0.200 minus X is about equal to 0.200. So what we can do is we can rewrite that expression where I'm essentially ignoring this part right here. That's going to make our math much simpler. We won't actually need the quadratic equation then. So I'm going to rewrite this one more time. 1.8 times 10 to the negative fifth is going to equal X squared over 0.200. And now we're going to solve for X. I'm going to grab my calculator. Please do the same. And I get that X comes out to be 0.00, we'll round here, 189. I'm just going to write down some numbers, 73. I do only want two significant digits, right? I have 2 here and 3 here. So I do only want 2 in my answer. Remember, leading zeros are not significant. So we're going to round that to 0.0019. And I'm just going to grab my calculator again and double check my math. I've been known to type stuff in wrong on occasion, as I'm sure we all have. Yep, feeling good about that number. So remember, we're not done, right? This is just X. If we go back up, we're asked to calculate the pH, which is going to be the negative log of my hydronium ion concentration, and then the equilibrium concentration of everything. So if I go back up, the equilibrium concentration of hydronium ions is X. That's also the equilibrium concentration of acetate ions. For acetic acid, I am going to have to subtract that from 0.200. So my equilibrium concentration for acetic acid, 0.200 molar minus 0.0019. And I get 0.198. Remember, we are subtracting, so it's digits after the decimal point. So here I have 3 digits after the decimal point. Here I actually have 4, so I want 3 digits after my decimal point. My hydronium ion concentration, 0.0019, and then don't forget units. And then my acetate ions is also equal to X. And I'm actually going to add one to this. Let's calculate our hydroxide ion concentration also. And we're going to do that using kW, right? Remember that 1.0 times 10 to the negative 14th is going to be equal to my hydronium ions concentration multiplied by my hydroxide ion concentration. So I'm just going to take this number and divide it into kW. So hydroxide ion concentration just typing into my calculator again. And for that, I got, for just 2 sig figs here, so 5.3 times 10 to the negative 12th molar. Cool. One more, we still have to do pH. And remember, pH is going to be the negative log of my hydronium ion concentration. Right, my hydronium ion concentration here is 0.0019 molar. and I get 2.72. Do pay attention to sig figs. Remember, we have that new rule for log values, only the digits after the decimal point are significant. So this is 2 significant digits, right? Those leading zeros don't count. So I want 2 digits after my decimal point. So even though I'm writing down 3 numbers, right, only 2 of those digits, 2 of those numbers are significant. So we have our answers here. We're going to do another example that's a little bit different, just kind of a twist on the idea. So for this one, we're going to actually be given the pH. So the pH of a 0.200 molar nicotinic acid, which is HC6H4NO2, is 2.78, and we're going to determine the Ka. So we're going to determine our equilibrium constant for this acid. So our steps are essentially going to be the same. We're just going to have to think about it a little bit differently. So I'm still going to write my acid dissociation equilibrium equation. I'm going to set that equal to my expression, right? I have just Ka for now. I don't actually have a number. We're going to make an ice table and then kind of think about what we have to do. So I'm going to write that the equation. So HC6H4NO2. And I should probably move that over a little bit. Plus water. Remember, anytime you're writing our acid dissociation equilibrium expression, it's always the acid plus water going to hydronium ions plus my conjugate base. So we're taking 1 proton, right, 1 hydrogen and a positive charge off of that acid to get me my conjugate base. And then because it's a weak acid, right, that conjugate base is picking up a proton from hydronium ions going in the reverse direction. And we know it's a weak acid for 2 reasons, right? It's not one of the strong acids that we were asked to memorize, but also I'm asking you to solve for the Ka, right? Remember, weak or strong acids don't have equilibrium constants, right? They don't exist in equilibrium, so we can't determine an equilibrium constant for something that doesn't establish equilibrium. So that's our second clue, right? The problem doesn't explicitly say it's a weak acid. Same with that last one we just did, right? If you're given this on a test or a quiz, it doesn't say weak acid in it, but we know it's weak because 1, acetic acid isn't on our list of strong acids, but also we're giving an equilibrium constant. We're not going to be given equilibrium constants for strong acids. So going back to my problem, I'm going to leave a little bit of space here. My equilibrium constant is my unknown, but we know that it's going to be equal to the concentration of hydronium ions at equilibrium. That's a horrible bracket. My conjugate base, also at equilibrium. Again, excluding water, it's a pure liquid. It's not part of my expression. Going back up here, initial change equilibrium. I know initially I have 0.200 molar. Water we're not going to care about, 0 and 0. And then this is where it gets kind of weird, right? We don't have Kas. If we go back and we look at this expression, this is my unknown, right? This is what we're asked to solve for. I also don't have these values, right? I have an initial concentration, but I don't have those. So if we go through and set, the minus x plus x sort of stuff and plug them in, I have 2 unknowns, right? I would have x and I would have Ka. I don't know what either one of those are just yet. Sorry, I'm just fixing what I just messed up. But it turns out we actually don't have two unknowns, right? We know our pH. If we know our pH, we actually know our hydronium ion concentration, right? And our hydronium concentration is X, right? If I would go do this, oops, not with a highlighter. If I would do minus X plus X and plus X, X is my hydronium ion concentration. If I know the pH, I know the hydronium ion concentration, I know what X is. So I actually don't have two unknowns. So we're going to use my pH to determine my hydronium ion concentration, which is the amount that we're dissociating or the amount that we're ionizing. So we know that if I was to take 10 and raise it to the negative pH, that gives me my hydronium ion concentration. So 10 raised to the negative 2.78. Grabbing my calculator here. Don't forget that negative sign. I get 0.00017. And actually my calculator comes out to 0.001659. I do only want two significant digits. Remember, 2.78 is a log value, so only digits after the decimal point count. So this is only two significant digits. So I do only want two here in my answer. I do need to put some units on there because that is my hydronium ion concentration. So if we go back up to our table, right? This is 0.0017 molar. And then this is going to be, we could actually go right to our equilibrium if we wanted, is going to be 0.200 minus 0.0017 molar, right? This is going to lose that amount. This is going to gain that amount. And I'm actually going to do that math. I'm going to take 0.2, so I'm grabbing my calculator here. I'm going to subtract 0.0017, and I get 0.198 molar. So now these are the values that we're going to plug in to my expression to solve for Ka. So 0.0017 molar times 0.0017 molar, so squared, over 0.198 molar. I am dropping my units because we don't need to show units with our equilibrium constant. If you wanted, I would have just molar for this one. So typing into my calculator again. And I get, oops, 1.5 times 10 to the negative fifth for my value for my equilibrium constant. So just kind of summarizing this one, if we go back up, I'm using my pH, right, that's given in the problem to determine my hydronium ion concentration. My hydronium ion concentration is the amount that dissociates, right? If we were to put the X's there, X is hydronium ion concentration. This is also X, so same concentration. And then my initial minus X. Then these were my equilibrium concentrations that we plugged in to that expression. One more thing I want to look at, and that's going to be percent ionization. The stronger the acid, remember, the more ionized it is. So the larger value we have for its percent ionization, the stronger our acid. You can also look at Kas, right? The bigger the value for Ka, the stronger the acid because the more products I have, right? If we were to compare, I'll come back to percent ionization here in a second, but if I was to compare the Ka for nicotinic acid to the Ka for acetic acid, wherever it is, going back up, they're actually really close, right? One is 1.8, the other is 1.5, both multiplied by 10 to the negative fifth. So I would say that they're really close to being equally strong. Acetic acid at 25 degrees Celsius is a little bit stronger, right? 1.8 is a larger number than 1.5. So at the same temperature, acetic acid is just a tiny bit stronger than nicotinic acid. And we get that just based on the value of my equilibrium constant. The other way to determine that is to calculate percent ionization. And that's just going to be the concentration of hydronium ions at equilibrium divided by my initial acid concentration. So an I here for initial concentration, and then the percents, we'll multiply it by 100. So if we want to calculate the percent ionization for my first example, we're going to scroll back up here and get some numbers. Again, please, if I go too fast, pause the video whenever you need to. So my initial concentration, 0.200 molar, and then my equilibrium concentration for hydronium ions, 0.0019 molar. So we need to remember those here for a second. Is going to equal 0.0019 molar divided by 0.200 molar multiplied by 100. So grabbing my calculator. Hopefully you guys play along. And I get 0.95%. For our second example, we'll do the same thing. I'm just going to take my equilibrium concentration of hydronium ions divided by my initial acid concentration. So going back up, this time we're going to have 0.0017 divided by 0.2 molar. And then it is a percent, so don't forget the 100. And I have 0.85%. So our initial concentration for both of these were the same, right? I started out with a 0.2 molar solution. And we had said that acetic acid was just a little bit stronger, right? Its Ka was just a little bit larger, 1.8 times 10 to the negative fifth versus 1.5 times 10 to the negative fifth. So starting out with equal concentrations, I would expect that acetic acid would be a little bit more dissociated, right, at equilibrium, and it is 0.95 compared to 0.85%. The stronger the acid, the larger its value for its equilibrium constant, right? Stronger acids have larger equilibrium constants, right? Larger Kas. So just kind of comparing to hydrofluoric acid has a Ka equal to 3.5 times 10 to the negative fourth. Hydrocyanic acid has a Ka equal to 4.9 times 10 to the negative 10th. So just based on those two values, we know that hydrofluoric acid is a much stronger acid than hydrocyanic acid, right? This is a larger Ka, larger value. So this is going to be my stronger acid. Both are weak acids, right? Both have equilibrium constants. I wouldn't be writing down equilibrium constants if they weren't weak, but hydrofluoric acid is going to ionize more than hydrocyanic acid is. We can express our equilibrium constants in a different way, and that's using pKa's. So a pKa is just the negative log of our Ka. Similar to the relationship between hydronium ion concentration and pH, right? As one goes up, the other goes down because it is a negative log. So the larger the value for my Ka, the smaller my pKa, because I do have that negative in there. So if I wanted to calculate the pKa for hydrofluoric acid, I'm going to take the negative log of 3.5 times 10 to the negative fourth. I'm just going to write both of them here, and then we'll do both at the same time. The negative log of 4.9 times 10 to the negative 10th, right? And that's going to equal my pKa. Because these are going to be log values, we need to take into account that new significant digit rule, right? Only the digits after the decimal point are going to count. So I'm typing into my calculator right now. Hopefully you guys are going to do the same. And I get 3.46, right? My calculator comes out to 3.4559. I want 2 digits after the decimal point for 2 significant digits, right? 2 significant digits here, 2 digits after my decimal point. I'm typing in the next one, and I have 9.31 for my pKa for hydrocyanic acid. So again, a bigger number, right? It's an inverse relationship. Let's actually write that down. Stronger acids have smaller pKa's, right? We established that hydrofluoric acid was stronger, right? It has the bigger Ka, it has the smaller pKa. So as acid strength increases, right, our equilibrium constant is going to increase, but our pKa, because it's the negative log, is going to decrease. So if you were given 2 pKa's and you were asked to pick which is the stronger acid, you would pick the smaller pKa. If you were given 2 Ka's and asked to pick the stronger acid, you're going to pick the larger, right? Larger, smaller.